4.7, L'Hopital's rule. Remember in L'Hopital's, we had a couple things that we had issues with when dealing with limits. So we're going back to limits. Remember we had this limit as x is approaching 0 of sine x over x. And earlier we just said we're just going to say by the graphing calculator and that we will prove later that its limit is 1. But otherwise, if we were to do direct substitution and we go ahead and did direct substitution, we would have 0 over 0, which is not allowed. So we call this indeterminate form. So it's the indeterminate form of 0 over 0. So there's got to be some way we can deal with finding this limit in a better way. And it turns out that we call it L'Hopital's rule. L'Hopital's rule is, suppose we got an f function and a g function that are differentiable on an open interval containing some a, where as long as the bottom or the numerator's derivative is not equal to 0, and we can then go ahead and say we can take the derivative of each of these top and bottom numerator denominator functions and then find its limit, provided that the limit on the right side exists or is from positive, negative, infinity. So the rule also applies if we're going to some a value or infinity value left or right. So it turns out that I can then use the sine x over x limit, and if I did L'Hopital's rule to it, which I will denote with this, and I'm going to go ahead and say as x going to infinity and take the derivative of sine x, which is cosine x, and then over the derivative of x, which is 1. I now can do direct substitution, which ends up being 1. And that's what we've known all along. So we can go ahead and say now by L'Hopital's rule, we can prove that sine x over x as x approaches 0 is 1. So we're going to go ahead, I'm going to do a couple of examples, and then we'll move on. So we'll do number 13. And 13 says, let's take the limit as x is approaching 2 of x squared minus 2x over 8 minus 6x plus x squared. This is, with direct substitution, a 0 over 0 indeterminate form, meaning we can't take this derivative. Or I'm not sorry, this derivative. We can't take this limit approaching 2. But if I do apply L'Hopital's rule, where I take just the derivative of the numerator, which would be 2x minus 2, over the derivative of the denominator, which would be negative 6 plus 2x, and then did direct substitution, I would get 2 over negative 2 or negative 1 as its limit. So as x approached 2, there did exist a limit for this problem. I'm going to go ahead and do number 23. And 23 says the limit as x approaches 0 of 1 minus cosine 3x over 8x squared. So I'm going to go ahead and apply L'Hopital's rule. And see that as x is approaching 0 and taking the limit of the numerator using chain rule. So the derivative of cosine, negative cosine, which would be negative of a negative sine x or positive, and then 3x, and then chain rule times 3. The derivative of the denominator would be 16x. At this point, I still can't do direct substitution. I still would get that 0 over 0 indeterminate form. So I'm going to have to apply L'Hopital's rule again. It's repeated. So I can do this until I get some values where I can actually find the derivative. If I can't, I can't. Then from here, taking this derivative, I've got the derivative of sine 3x is cosine 3x. But I've got 3, and then I've got that was there from the original, and then taking the chain rule again times 3. And the derivative of the denominator is now 16. So then I now have, I could do direct substitution, would be 9 times cosine, well, 3 times 0 would be 0 over 16. Cosine of 0 is 1, so I have 9/16 is my answer. I'm going to do one more in this section, and we're going to do 33. And 33 says the limit as v approaches 3 of v minus 1 minus the square root of v squared minus 5 over v minus 3. Doing direct substitution would give me the indeterminate form of 0 over 0. And if that's the case, I'm going to apply L'Hopital's rule. So I'm going to apply L'Hopital's, and now remember, it's just the derivative of the numerator over the derivative of the denominator. So if I'm going to go ahead and say the derivative of the numerator would be 1 minus v, 2v because of the chain rule, and doing the square root would be 2 over v squared minus 5. The 2's are reducing. All right, the derivative of the denominator is 1. So I could, in a sense, rewrite this as this. If I wanted to do direct substitution from here, I could, I think I could. If I did, I would get 1 minus 3 over square root of 9 minus 5, or 1 minus, and it should be 3 halves. And then from here, I see 1 minus 1½ is really a negative 1/2. And that is my answer there. L'Hopital's rule applying when it's an infinity over infinity as its indeterminate form. It's saying the same principles. We go ahead and do the same thing. So I'm going to go ahead and just do going on to the next thing, which I want to talk about related forms of this one, which is 0 times infinity and infinity minus infinity. So I want to go ahead. We want to put this in or recast into a 0 over 0 indeterminate form or an infinity over infinity form. So when dealing with these two special cases, I'm going to go ahead and try to do example number 45. And example number 45 says the limit as x approaches 0 of x cosecant x. And right now, because it's a multiplication, it's kind of like, how do I deal with this? I'm going to go ahead and put this, recast this, is how the book puts it, into a form of f of x over a g of x. So in this case, I could sometimes do the x and using the reciprocal form of saying it's really multiplying 1 over x, and or divided by 1 over x, or in this case, because of the cosecant, I may change that one and say it's really, the cosecant x is really sine x in the denominator. So I'm going to go ahead and use this, and if I do direct substitution, I now have it in the indeterminate form of 0 over 0, and then I can apply L'Hopital's rule. So I have the derivative of x and the derivative of sine x, and then I can do direct substitution, which would be 1. So the procedures for the indeterminate forms of 1 raised to infinity, or 0 raised to 0, and infinity raised to 0. We're going to need the change of base. We need to recast these functions into some function that we can go ahead and do its derivative. So let's go ahead and review that the change of base back from the logarithm section was if had a function b raised to x, we can rewrite it as e raised to x ln of b. And then we can use that form. So it says here we're going to analyze L, the limit of these two functions, and where we took f of x raised to g of x and applied the logarithm, and we changed the base. This limit then can be in the form, put into the form of 0 over 0, infinity over infinity, which can be handled by L'Hopital's rule. From there, once we find this L, this limit, we're going to set it equal to e raised to this L we found. And if it's infinity or negative infinity, we can have that, or it can be to 0. So we're going to go ahead and try one of these. We're going to do number 63. I'm sorry, it's going to be 61. We have that as the limit as x is approaching infinity of the quantity 1 plus a over x raised to the x. And this is in the form, indeterminate form of 1 raised to infinity. So it's going to be for a constant a. Okay, so a is just a number, pretend. So we're going to go ahead and try to deal with this. So we're going to do step 1, which was we're going to go ahead and do this change of base. So it's really going to say we're going to take this and put it into the change of base form, which is e to the x ln of 1 plus a over x. So we did this change of base. We're going to take basically the log, take the log of this limit, and then we can see that L would be the limit as x is approaching infinity of x ln of 1 plus a over x. And we're going to go ahead and put this into an f of x over g of x form. So I'm going to go ahead and put the x in the denominator by multiplying by 1 over x for both the numerator and the denominator. And I get the limit as x is approaching infinity of ln of 1 plus a over x over 1 over x. I now have an f of x in the numerator and a g of x in the denominator that I can now apply L'Hopital's rule. So I'm going to go ahead and apply L'Hopital's. For my numerator, I should have 1 over 1 plus a to the x. Using chain rule, though, I now have it multiplying negative a over x squared because this is not just x, and we're going to apply chain rule. The derivative of the denominator is negative 1 over x squared. So you have to take each numerator and denominator's derivative. And then I'm going to go ahead and simplify this by multiplying by the reciprocal. So I really have negative x squared over 1. And so I can lose this denominator. And then I can see that this would simplify here. And I now have the limit as x is approaching infinity of 1 over 1 plus a to the x times a positive a. And now I have no issue with doing direct substitution in a sense, remembering it's infinity. So remember when we have an x in the denominator and we're substituting in infinity, that this should be approaching 0. So this first term is now really going to be 1, and a is a constant. So my answer is A for L. That's only step 1 of finding this L'Hopital's limit. So we applied L'Hopital's. The step 2 said we're going to go ahead and take E and raise it to the L. So in this case, it was E raised to A, and that is the value of my limit for this function. All right, moving on, we're going to do growth rates of function as x is approaching infinity. So in this case, it's important use of L'Hopital's rule is to compare growth rates. In your book, page 316, there is a lot of information that I would like to talk about. A particular theory for modeling the spread of an epidemic predicts that the number of infected people t days after the start of it is given by a function where there is t squared in the numerator and e raised to some t with a rate of 0.01 with the t. And which one grows faster? Is this epidemic? The question is it going to, as t keeps going on forever, does the epidemic spread or does it die out? It becomes which function is growing faster, the t squared in the numerator or the e to the t in the denominator. Another one is prime number as in integers where p is greater than or equal to 2 has only 2 divisors, 1 in itself. The first few prime numbers are 2, 3, 5, 7, 11. And a celebrated theorem states that the number of prime numbers is less than x approximately as x over ln of x. So the question is, according to this theorem, is the number of prime numbers infinite? Which one's growing faster? So there's a ton of applications in wanting to know how fast certain functions grow and at what rate. So we have a slew of functions, and what we're going to do is make sure we set it up in this situation and apply L'Hopital's if we need to. So in here, in this first one, if I plug g of x as the numerator and f of x as the denominator and it goes to 0, it means the denominator, or f of x, grew faster. It was like having a constant in the numerator and then plugging in an infinity in the denominator, we approach 0. And then it says equivalently, if we stick f of x in the numerator and g of x in the denominator and goes to infinity, it still means f of x grew faster. It depends where you plug into the numerator denominator which function and how this value goes. If it goes to an actual number where m is non-zero and finite, it means they're comparable growth rates. They're growing at the exact same rate. So I'm going to do at least one example, and there is a list on the next page that does list growth rates. So for this one, we're going to go ahead and do example 69, given x to the 10th and e to the 0.01x. We want to compare which one grows faster. So I'm going to say as the limit where x is approaching infinity, and I'll put x to the 10th over e to the 0.01x. And then I'm going to apply L'Hopital's rule. I get 10x to the 9th, and it'd be 0.01 e to the 0.01x. So I'm going to see that, well, that doesn't really help me. Oops, I lost my limit. And I would go ahead and I'm going to repeat this and repeat this. And if I keep repeating, this polynomial numerator will eventually get to a constant because I would have to take the derivative 10 times, 9 times to find that this would go to a constant. So this one goes to a constant. then this one, because it's e, and e will always be raised to that, yes, this 0.01 would have to be multiplied by 0.01 again. But remember, this is really a fraction. So it's like saying in my denominator, and then this would be a reciprocal multiplication to simplify that fraction. So my question is, this e will never go away. It is going to continue to be there. So if that's the case, if I start holding the numerator as a constant and e keeps growing, then this is the case where this function, the limit will go to 0. Therefore, e to the point 0.01x grows faster. So some of these you would have to do many calculations or think through this logically. So my last thing is ranking growth rates as x is approaching infinity, where the double arrow says that f grows faster than g, means that g grows faster than f as x is approaching 0. So f is growing slower. G means that g grows faster than f. Okay, so it's saying this one's faster, whatever you want to put here. All right, so it has here with positive real numbers p, q, r, and s, and b is greater than 1. We have a linear power function, a power function where the two are combined, where we have another power function where it's added to something, an exponential function, and an x raised to an x. So out of all of these different functions, this one is the fastest one in the group. This one is the slowest. So you can almost know and practice and learn some of these and when things grow faster or not.